Yield lines, special cases. This video will deal with square slabs with 1 point support and 1 fixed end support. You will see here a square slab. One is a simply supported edge, the other is a fixed end support and a point support on the other side, loaded with an uniform distributed load of Q kilonewtons per square meter. We are now looking for the maximum bending moment by means of yield lines. We have to determine the axis of rotation. So this is at the support. It is one axis of rotation. This is the second one. And one axis of rotation goes through this point support. There is no symmetry from this axis, so we do not know what this angle here is. We know that the yield line must be at the crossings of, or at the intersection, sorry, of the axis of rotation. So it's somewhere here, but the angle alpha 2 and alpha 4 is not known. Alpha 2 because this gives you the angle of the yield line, and alpha 4 plus alpha 2 gives you the angle of this axis of rotation. The same happens on this side. Again, this angle we do not know. It's even worse. This angle is different from this angle because there is no symmetry. So this is alpha 3. This is alpha 5, but this can be expressed in function of alpha 3, alpha 2, and alpha 4. So we have here 3 parameters. This is the direction of the yield lines, or the center lines of the yield lines. We can draw now the yield lines. This is at the fixed end support. This is for the yield line at the top of the slab. And the other is, of course, starting as the cross section here and joining the cross sections of those two yield lines. We will, of course, assume here in this example that the bending moment, that the negative bending moments are equal to the positive bending moments. But you can fill in for this yield line M or fraction of M you can choose. Parameters for the optimization. We have x2, which is the tangents of alpha 2. We have x3, the tangents of alpha 3, and x4, the tangents of alpha 4. You can also take a parameter, which is this one. Instead of, for instance, alpha 4 or instead of alpha 2, you can also take this as a variable. But because we have chosen alpha 2, 3, and 4, this is fixed, this point is fixed, and this point is fixed. So the angle here is can also be expressed in function of the other 3. The goal is now to express all parameters in function of alpha 2, or in function of x2, x3, and x4. So we have 3 parameters to optimize the function. We will do that by using some trigonometry formulas, like the summation of tangents, the rule of sinus alpha in function of the tangents, and the formula of cosine alpha in function of the tangents. We can now identify different variables, and we will try to express them all in function of x2, x3, and x4. You can start with, for instance, S7, which is from there to there. So it fixes this point, this cross section there. So this side S7 can be easily done in function of the tangents of alpha 3. And you arrive at this expression. Same for S8. We have this expression. S1, you can also express it in x2 and x4. The same for S2, and S4, and S5. You see, it's getting sometimes a little bit complicated, but it is in fact straightforward trigonometry that you can use to calculate all parameters in function of x2, 3, and 4. The distance S10 is then given by this formula, S9 by this formula, and x1, like we said, this is the tangent of this angle, can be expressed in function of x2, x3, and x4. Then we arrive at A1, A3, H1, and H2. So you will see H1, for instance, is expressed with the cotangents rule, which is A plus S8, is this side, divided by the cotangents of this angle and the cotangents of this angle. So the cotangents is 1 over x1 and 1 over x2. And then S8, we already calculated it, and you can express it in function of x1 to x2, 3, and 4. Same happens for H2. For H3, we also use the tangents rule, but it's getting a little bit complicated to write down the formula. That's why I used some sub-formulas like this, and then every parameter is then expressed in x2, x3, and x4. Now, we can calculate the work done by the external forces using all those parameters that we have defined. The parameters that I used in this formula, I've given it a blue color. So the work done by the external forces is E over Q delta. And you will see that the whole this situation can be expressed in function of triangles. So it will be this triangle, and this triangle. So everything is a sum of triangles. Of course, when you take, for instance, this triangle, you will take the total minus the portion outside the slab, but it still is a triangle. So everything is a summation of triangles. So it means that the mean deflection is delta over 3. So that's why this 1 over 3 is here. So we can now look at the first portion, which is this triangle. So the base is S7 plus A times H2 divided by 2 for the surface of a triangle, minus this portion, which is S7 multiplied by A3 divided by 2, and the maximum deflection of this is, of course, A3 divided by H2. So that's this term here. Then for the other side here, we have H1 times A plus SB divided by 2 for the surface of the triangle, minus the portion outside of the slab, which is 8.1 times S8 divided by 2, multiplied by the maximum deflection on this point is, of course, A1 divided by H1. And then we got the third part, which is H3 times S2 plus S1 divided by 2. And I have to subtract this triangle from it and this triangle, which is stated there and there. So it's in fact relatively simple, but it's getting difficult to write it all down explicitly in one formula. So I didn't substitute every variable or every parameter. I just simplified a little bit this formula, and you arrive at this expression. If you put in A1 in function of x2, x3, and x4, you will have a very lengthy formula, which is dangerous to use. So we use this expression. The work done by the internal forces is more simple. For instance, for this yield line, I project this to this axis of rotation. It means that the length is then A multiplied by the angle of rotation, which is delta divided by H1. So that's this. The negative bending moment is the same. It's A divided by delta over H1. On this side, this is projected to that axis of rotation. So it gives you A divided by H2. And then, of course, those yield lines projected on this axis of rotation gives you S5 plus S4 divided by delta over H3, which is this expression. So it means now that we can express, because E is equal to D, we get M, and M is then a function of alpha 2, alpha 3, and alpha 4, or it's a function of x2, x3, x4, is the same. But working with the tangles of the angle is a little bit more difficult to make an interpretation, so I just expressed this in function of alpha 2, 3, and 4 in degrees. And it's equal then to Q times E over D, and E is also a function of alpha 2, 3, and 4, and D also. Now, we can, for the bending moment, now we need to maximize this in function of those three parameters. But not every combination of alpha 3, 2, and 4, and so on is valid. So it must meet conditions, and the condition is that H1, of course, H1 must be smaller than A, so it means that this point cannot be outside. So this point must be inside the slab, which is logic. And H2, the same thing, this point cannot be outside the slab, so H2 must be smaller than A. So that are the conditions. You can maximize this function by means of a computer program or something like that, but we will do it in a more simple way. We do it just visually. And to do so, we need to make some graphs. And in the graphs, Q is taken as 1 kilonewton per square meter and A is taken as 5 meters. It does not matter because this is a scale. It's in fact a scale of 2Q8 squared, so it's a scale 25. Now we can make a graph of, remember we have to maximize the bending moment M, which is proportional to E over D. So first we will look at E in function of alpha 2, alpha 3, and alpha 4. When we make some plots like that, you will see that, for instance, for alpha 4 equals to 10, and alpha 3 going from 10 to 30, and in function of alpha 2 from 20 to 50 degrees, this is degrees, you have different curves. Out of those curves, you see that to maximize M, that M decreases with decreasing E, so it means that E decreases also with increasing alpha 2, so M decreases with increasing alpha 2. So we know that we have to look at some values somewhere around here, and the range that we look is alpha 2 between 2 and 50 degrees, alpha 3 between 20 and 25 degrees, and alpha 4 between 0 and 20 degrees. In fact, it's very simple. I've plotted many of those curves and look for a maximum. D, M is E over D, so it means that to maximize D, M increases with decreasing D, and D decreases with increasing alpha 2. So now alpha 2 must increase to make M maximum. E was the opposite, but this is more determined. And you see that alpha 2 between 20 and 50 degrees, alpha 3 between 20 and 25, and alpha 4 between 0 and 20. This is an assumption that we find the maximum within this region. So we said, when I'm plotting M, the scale is 25. Then you can see that within the range that we said, we plot different curves. And you can easily see that they reach somewhere a maximum, but it's not very easily to see it visually, but we are very close. You see that, for instance, on this is already decreasing the maximum. So this is already decreasing. The maximum is found here, and it's alpha 1 40, alpha 2 40, alpha 3 30 and alpha 4 10 degrees. That gives you the maximum. Now we will check this, if this is the case. Or we would check first the validity of this value. So it means H1 must be smaller than A. Remember, A is 5 here in our example. So for those values of the angles, H1 must be smaller than 5. So it is smaller than 5. H2 2, so that's okay. Now we check this 40, 30, and 10 degree solution we test, for instance, the 40 degree of alpha 2 against the alpha 4. And so you will see that when alpha 40 and 10, it is still the biggest. So you see that the maximum is rising up and going down again. So this is okay. And this value is the check on alpha 3, and alpha 3 is then here 30 degrees. So this is the maximum of this function. We can now look what the result is. If you plot the axis of rotation, then you see that you have yield lines doing like this. With QH squared 25, the bending moment is 1.814. You can express it in a different way by saying M max is equal to QH squared, the scale, divided by 13.8. It's just like that. And it looks like here. So at the maximum is achieved by alpha 2 40 degrees. Alpha 4 is 10 degrees, so this is 50 degrees. Alpha 3 is 30 degrees, and this is 10 degrees, so this is 40 degrees. 40 and 50 is 90, so that's okay. This solution is good. And this is 52 degrees. Now, when you are using the 30, 45, 60 rule, it should be, in fact, 60 degrees, because this is simply supported and this is fixed. So then this would be 60 degrees. So, but by optimization, you find 52.